everyone, and welcome to lesson 1.4. Today we are going to talk about inductive reasoning and how we can use inductive reasoning to make conjectures about relationships. So with our first part here of this lesson, we notice that if there is a point on a circle, we have one region. If we have 2 points in that circle that we connect, we end up with 2 regions. If we have 3, we start seeing that there are 4 regions. And then if there are 4, we start noticing that there are 8 total regions. So how does the number of regions change when another point is added? What patterns are we noticing? Well, hopefully you said when you notice that these patterns are happening, it appears to double as each point is added. We seem to have doubling regions as time goes on. Well, we want to check out in our next example, if we have 5 points, how does that work? Well, we start connecting here. We have 1, 2, 3, 4, connect there. 1, 2, 3, connect there. 1, 2, and then connect here as well. So if we count these out, it's kind of messy, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and again, 16 total regions. So does it appear that our prediction is correct? The answer is yes. With that prediction, it appears with 5 points on our circle, there are 16 regions. So what we've done is we have used this process of inductive reasoning where we start seeing these patterns based on specific examples and events, and we inductively decide what the next thing will be in that certain pattern. So for instance, we see down here that each time it looks like our pattern is decreasing specifically by the number 6 each time. And we could double check that, like we could take this term and subtract away the first term. So 82 minus 88, we see we subtracted 6. Do that again with this one. We do, 76 minus 82, we subtracted 6 to keep going down. So our next 2 terms, if we subtract 6 more, 2 more times, would be 58 and 52. Same idea on example B. This time, though, we're not adding or subtracting a consistent number. This time it looks like we are adding 2, then 4, then 6, then 8. So each time we're adding the next even number. So we're adding 10 to get 33, 12 to get 45 in that particular pattern. All right, in these next 2 examples, it appears that our first one, we are getting smaller each time. Right? In fact, we are dividing by 2 each time to get successively smaller. So our next 2 terms, if we divide 100 by 2, we would have 50, and then 50 by 2, we would have 25. The next pattern is a little bit trickier because notice we eventually start turning into the fact that it looks like we are going to be having a fractional value. So sometimes either we could be subtracting, but notice we went, we're getting larger. We went up by 6, and then we went up by 8. So that didn't really make sense. And we see this fraction happening. So one way we can see with dividing what our pattern is we could take term 2, which is 24, and divide it by term 1. And we can see if we turn this into a fraction, that each time we are multiplying by the fraction 4/3. So we could check this out. Watch, 18 times 4/3 gave us 24. 24 times 4/3 gave us the 32. Times 4/3 again. We see this fractional value. And we keep going to see that our next 2 terms, if we multiply it by 4/3, again, we get 512 over 9, and then 2048 over 27. So that was a little bit trickier. But again, we can see these interesting patterns as time goes on. The next one, do you notice a pattern and what could be happening each time? Well, hopefully you're noticing that we added 2, then we added 3, then we added 4. So next we would add 5 to get a term of 8, and then we would add 6 to get a term of 14. Part B is asking you to make a conjecture. Here is the number of members on the chess team in years 1, 2, 3, and 4. If this continues, what would be the amount of chess members on the 6th year? Well, hopefully what you are noticing each time we added 3, then 4, then 5. So for year 5, we would add 6 people, that'd be 28. And then for year 6, we had to add 7 for a total of 35 members. Would be our prediction. Last but not least, notice that this one is getting positive and negative, going back and forth, and it's increasing. So notice what we're actually doing. Again, we could test this out. If we divide to go back and forth, we would be multiplying by a negative number to get it to jump from back and forth, positive and negative. And each time we're actually multiplying by -3. So if we multiply 1620 by -3, we get -4,860. And then the last one, 14,580. Now, inductive reasoning is a type of reasoning that makes its conclusion based on patterns and specific examples, and they make what we call a conjecture. Okay, now these conjectures, we notice, is an unproven statement or rule that is based on inductive reasoning. It's what we would call a generalization, or sometimes we would just say it's a prediction. But we haven't officially proven it to be true. It may or may not be true. So sometimes with inductive reasoning, we see that not every conjecture is true. We can disprove them sometimes with just one counter example. Okay, you could say, okay, no, this pattern is not working because of this one example that just disproved the whole statement. Okay, so for instance, if I see on the top of the next page that if I have 4 sides to my figure, I have 2 diagonals, Lola here is predicting that each polygon will have 2 fewer diagonals than sides. So she's predicting if I have 5 sides, I should have 3 diagonals. Well, let's see if Lola is true. That's the prediction, right? So she takes 1, 2, 3, 4, 5 total diagonals. So was Lola true? The answer here is no. Okay, no. Okay, the pentagon has 5 sides and 5 diagonals, not 2 fewer diagonals. Okay, she should have had 3 if her pattern was going to hold. Let's try another one. This time it says that Mila flips a coin 3 times. She decides she gets tails each time based on this pattern. She says that all the time she flips a coin, she's going to get tails. Do we believe this is reasonable? Why or why not? Hopefully you see here that no, okay, there is always a 50-50 chance of getting heads or tails when you flip the coin. So just because she had 3 in a row does not mean it will continue. Our last example together shows that we have this table here, and it's showing all the calculations for the input values for -2, -1, 0, 1, and 2 to this function here, 2x plus 5. And Liam states that based on the values shown in the table, f of x is always positive. Do we think he's true? Well, a little less, a little yes, a little no. Like if we keep going in this pattern for these bigger numbers, we see that this is in fact getting more and more positive, right, each time. The problem is the table didn't show us going this negative direction, because officially then we would have been getting negative numbers when we plugged it in. Okay, so that's why this is misleading information, because the table doesn't show more negative x values that would use that would have a negative f of x value. So again, for instance, in an example of a counterexample to prove this wrong is that if we plugged in -5 for our pattern here into this, we would take 2 times -5 plus 5. So -10 plus 5 is a negative number. This disproves Liam's conjecture that it's always positive. So that's why Liam is wrong. Okay, so we would say no for our answer there. Try the last one on your own and see what your reasoning is. We'll work more with these predictions in class and looking at the patterns. Thanks, everyone.